Okay, secondary educators, we have been looking at exponents and logs and complex numbers, so it makes sense to talk about complex logarithms, what we mean when we talk about the logarithm of a complex number. And to do that, well, we got to remember where we came from. We remember that we started with some number a plus bi, and then we plotted that as a point in the Cartesian plane AB. This is the rectangular point AB. And then we said, wait a minute. That's some distance r from the origin, r for origin, and there's some angle theta of rotation. And so we could think about this as the polar point r theta, polar, and then that turned into r times e to the I theta, which turned into r times cosine, whoa, I'm so sorry, r times cosine theta plus I times sine of theta, right? And all of these work together to express the same complex number. So all fine, that's all fine. So what do we mean when we talk about the log of z? Well, the log of z is the log of r e to the I theta, and that's a product, so it's the sum of two logs. That's as far as we can go. This is a log base e, right? So we have that the log of z is this quantity, which is a little bit weird to think about. But I'll remind us of a couple of things. This is the distance to the origin from the point AB, and this is the angle of rotation. And then we'll pause to consider why that's a weird definition. This is the angle theta, but this is also the angle theta, and this is also the angle theta. There are lots of thetas that connect to one particular point in the complex plane. So the log of z, the log of a complex number, there are many, many possible values because there are many, many possible thetas. And I'll show you what I mean. We'll find the log of e to make sure that that still works. Then we'll find the log of I to make sure that that works. And then we'll find the log of -1 to make sure that that works. And just as a reminder, the log of a complex number, the log of a plus bi, is the log of r plus I theta, where the r and the theta are as they are in the polar grid. So in this case, the log of e is the log of however far e is from the origin in the complex plane plus I theta. Well, where is e in the complex plane? It's right here. So the log of the real number e is 1, and theta could be 0, or it could be 2 pi, or it could be 4 pi, or, and we just keep going. It's an interesting thing to think about. Where's I in the complex plane? Here's I in the complex plane, right? That's 0 plus 1i, right? So when we find the log of I, That's the log of the absolute value of I, the distance I is from the origin in the complex plane, plus I theta. Well, the distance of this point to the origin in the complex plane, that's 1, and the log of the number 1 is 0, plus I theta, where theta is pi over 2, or 5 pi over 2, or 9 pi over 2, or and so on. Those are all possible thetas. And then we consider -1. Well, here's -1 in the complex plane. So we find the log of the absolute value of -1 plus I theta. Well, the log of the absolute value of -1, that's still 0, plus I theta, where theta is pi or 3 pi or and so on. Those are all possible values for the log of -1. Okay, so complex logarithms are based on the notion that we can plot a point in the complex plane, we can figure out how far it is from the origin, we can figure out what its angle theta of rotation is, and we can apply what we know to be true. Hope that's helpful. Powers of complex numbers coming up next.